We're having this issue in other classes, so I want to address it, although I don't think it'll be as big of an issue in here. Math book, although you don't always need it, like your group, your team, or whatever needs to have like 1 or 2 books at your team. Because you can't just rely on me keeping it on the screen, because I move around, I do multiple things. So when I went to like go calibrate my board earlier, and nobody in the class had books out, it was like everyone had to sit and wait and do nothing, because they didn't have a book to be able to look at on their own. Everybody should have pencils in their binder, in their pencil pouch. And if you don't, you're going to have to ask me for it, because I don't have any extras sitting out right now, because that's not my job. It's your job as a student to have pencils. You're burning through all our class sets of pencils ridiculously fast. Homeworks, like when it comes to homework collection, I don't like, it's this assignment to that assignment. And you're like, oh, what were those? Like, what numbers? I'm not answering that question anymore. We're in quarter 2. You should be filling in your plan book. If you are choosing not to fill in your plan book, that's a poor choice that you're making, and you're going to have to own when it bites you in the butt. So if anybody this morning has made the choice, I'm not going to fill in my plan book, please fix that choice right now and fill in your plan book. I'm giving you a ton of time. Like, what I'm worried about is the people that I see sitting doing nothing. Like, Simon, I'm going to pick on you. Like, is your playbook filled in? Or your notes? Do you have a header on your notes? Are you ready to go? Also, some people, like, I still have papers being turned in with no names. I have 5 things over on my no-name board. Come on. It's quarter 2 now. We've been here for 2 months. The other thing I need to make sure we address is we need all of the math textbooks to come back here. So if you're taking one home at night, that's okay, but it needs to come back and like live in my room for the day. I'm trying to figure out, and we still haven't gotten the new books in, Connor. I'm still waiting. I'm starting to lose faith. Somebody else might have grabbed it. It's okay. But at the end of class, like, we need to make sure that all the books are back on the rack. I need to someday be able to account for all books and figure out like what we're missing and exactly how many we need now. So as you're finishing, getting set up, I'll just go ahead and read this. So in this course, we've looked at several relationships between 2 sets of information. Normally we reference like an input-output, something like that. So to continue our investigation of proportional relationships, we'll look at the mathematical relationships between distance, rate, and time, which actually comes to a great... I'm not going to give you the formula yet. I've got a formula that I call the DIRT formula, and it's really useful, but I think we're going to find that out through class today. So later in the final section of this chapter, we'll identify proportional relationships and use our understanding of proportionality to solve problems. So if you've ever asked the elusive, are we there yet question, my favorite answer for that is, I don't know, calculate it. Because you can always calculate exactly how long it will take you to get somewhere, assuming that you stay at the same speed, which of course we know is not realistic, but we can get pretty darn close. So, George. Right, George is standing on a platform, and he waved goodbye to his sister as she left for summer camp. Later, as he was getting in his car to drive home, he saw a light flashing inside the train station, and he heard an announcement that his sister's train had malfunctioned and was stuck on the tracks. George had a map of the train's route and decided to drive to where the train was stuck and pick up his sister. How could George be able to determine where the train is? What information would he need, and how do you think we would use it to figure this out? So for a minute, I just want you to talk with your group. Then I will let you ask me questions about the situation and give you another minute to try to figure out how far they... So the first thing you need to talk about as a group is what questions would you ask to try to figure out this situation. So if we were going to determine where George's sister's train is, what would we need to know?
Was there speed behind it?
And cut. What questions do you want to ask? The train goes a maximum of 50 miles an hour.
What is the distance between point A to point B?
We don't know that. That's what we're trying to figure out. Like, the distance that the train needs to travel doesn't matter. It broke. Right? So what we need to figure out is how far did it get so that George can figure out how to get to his sister. George?
What was the time that it took from point A to the mountain?
What was the time? So right now we know the rate of the train was 50 miles an hour. And let's assume, to make your life easy now in high school, you won't be able to make your life easy, but let's assume as soon as the train starts, it's going 50. And as soon as it malfunctions, it stops immediately. So if you've been on Top Thrill Dragster, you know in the less than a second that you get up to your speed, you're immediately going that speed. Let's assume this train gets accelerates as fast as Top Thrill Dragster. So your rate's 50, and the time that it had been traveling was about 90 minutes. I need you to figure out how far down the track the train is. You have 1 more minute. Yeah.
So like 60 minutes an hour. Time already. Wait,
31, 80.
distance actually
75. Oh, yeah. You're like, I don't even care about 75. How does this go to the train station?
5 seconds. And time. Braden. I mean, I can switch it to Braylon if you want. I'm just doing it. So, Braden. I'm trying to find where people are. What'd your team do?
I taught them about the Dorito tactic the entire time, so we didn't. What is the
You know, you can start a fire with Doritos.
Yeah, no,
Yes, they are flammable. Okay, so moving on to a different group then. Gabe. Well, that doesn't help. Gabe, do you have any other thoughts aside from Dorito tactics?
Well,
George!
Yes.
Pass.
Oh, what?
Oh,
No, I didn't say pass,
oh,
I said
okay.
yes.
Okay.
So, our group, we did the rate times the time and got 500.
Now, did you do 50 times 90?
What?
50 times 90, right? You got like 4,500?
That doesn't sound right.
Well, you just said you did the rate times the time.
Yeah, I don't know.
What'd you get?
Yeah, we got 4,500.
Wow, that train traveled far.
Yeah, I know.
You know how far 4,500 miles is?
I know that's not so fast, but
Now, what I've realized, I was kind of making this joke with my buddy Dave, well, you guys know Dave. I was making this joke with Dave this weekend, that I feel as if I've become a really good hunter, because I know where to set the traps for you guys. We don't want the time in 90 minutes, and most people wouldn't say 90 minutes. Jessica, what's the issue here? This is referencing hours, which means this is no good. We need hours to be able to talk about our time. So if we want to multiply the rate times the time, I agree, that's perfect. But your units have to agree. So hang on just real quick. So here's the formula. Here's what I nicknamed the DIRT formula. You'll understand why in a moment. Just do you trust me? Distance D-E-R-T. Distance equals, so not D-I-R-T. Distance equals rate times time. So really, actually, if you want to think about what the word would be, it'd be D-E-R-T-T. Dirt. Distance equals rate times time. So we are going to test this out. However, I am trying to save the school's copy code this year, and like I've already told you, we've used up way too much money on copies. So all of us need to make a graph on our paper, which really you're probably going to want a blank sheet of graph paper. So if you have a new one, flip to that or flip to the back or something like that. You want to make a graph that goes with the size of your page. The bottom, hey, it doesn't take talking to get a new piece of graph paper. The bottoms are time, and it needs to go to at least 20, but please don't, like, just make it real small. Like, spread it out. This uses every 2 boxes is worth 1 second. You could do 1-to-1 if you wanted, but they use more of their paper. So we only need to go up to 20 seconds. At max, you could go to 30, but you don't really need to do that. So with the width of your paper, and you might use a ruler like Jessica's grabbing to make your axes nice and straight, if you care about that like I do. Then your distance, we're going to put tick marks every 5 boxes, but we don't yet know what we're going to label. We know it's going to be centimeters, but actually all of you are going to have unique graphs because I don't have 6 of the same toys. I'm not joking. Braden like just locked on me and melted my soul to toys.
Somebody say toys.
So, your team, your mission, if you choose to accept it.
Mission Impossible.
Sweet, this works. Your team's mission will be to send 1 person. How many people? 1 up here to retrieve 3 items. 2 yardstick or meter sticks. You would like them to agree with each other. Now, well, actually, I take that back. You don't need them to agree with each other. What you're going to end up doing with these is essentially making a little track. So you're going to have 1 on each side. Now you want 1 turned so that the numbers are towards the middle, and you want your toy to start at 0. So you're all smart people. You can figure out how to set the meter stick to make this work. Then, those are 2 of your items, right? 2 yardsticks or meter sticks. Now, it doesn't matter if you get your measurements in inches. We can convert. There's 2.5 centimeters, 2.54 centimeters per inch. So if you get inches, 1 inch equals 2.54 centimeters. So then we can just convert. Take your inches and multiply by 2.54. And then you're going to take 1 wind-up toy. Here's what you're going to end up doing, because I need to be able to release you so you can do this work. Your task is 1, you have to notate what your wind-up toy is. So this is like Blue Robot Dude or whatever you want to call him. And now I'm going to like give you the timer. And actually, if nobody's out in the library, we're probably going to go take over some library tables. You're going to set your toy at 0. And when I say go for the timer, you let it go.
My sister has that.
So this one might be broken. Alright, so this one's broken. And this is why this is tough.
I am machine.
Alright, smaller Blue Robot. This is tough because these toys aren't very good. So, hold up. When I say go, you let your toy go.
It's so slow.
And we will let it travel for 5 seconds and potentially 10 seconds. Now, a lot of these can't go for 10 seconds continuously, so that's why we do 5 seconds. We're going to do this a few times and then average it. Right? So you need at least, hey, why are so many eyes not on me? You need at least 1 person documenting how far things go. Okay? So if you're the documenting person, like maybe you have one person is your toy like I gotta let the toy go, so maybe I'm not documenting. But then maybe another person's like watching on the side, like when I say time or 5 seconds, or you like mark your spot, and really we'll probably just do 5 seconds because I don't think these guys will go for 10. And if it gets a weird line, it might run up against this. It's okay, but we're hoping it goes forward for 5 seconds. A couple of the ones that jump as they go, if it falls over, obviously you gotta try again. But yeah, that is what we're doing. So you have 30 seconds to make that one person is coming up. The toys are here.
Okay, I'll go.
And actually, we're going to stay in this room. Hey, I get it. I gave you toys, but come on, you're in 7th grade. Clear off one of your desks. Clear off one, or you guys just clear some space so that you can put your meter sticks, or a group or two can also go to the back table. There's enough space back there for 2 groups. Decide if you're on a slanted desk, decide if you're gonna go up or downhill. Like that's up to you. If you're on the flat desk, it should be easy. Lay out your tracks. Right, your borders. Lay out your tracks. You're probably going to want to either go uphill or down, not like sideways. Yeah. So we might need to stand up. We might need to move. Make your tracks. Get your 0 point. Make your tracks. Get your 0 point. Clear off one of your desks. Somebody's got to document it though.
We need the timer. Oh wait, that's the timer.
Are we ready? Alright, what needs to happen? One person is the toy winder, and you're going to release your toy. At least, hey, and if you way over crank these, you will break it and ruin it for other class, so please don't. If you way super over crank this, you will break it. One person to release the toy, one person at least to make note of how far it went, and then another person needs to be writing things down. Okay, we're going to do this at least 5 times. Are we ready? Yeah. Release. Hey, this won't work if people cannot hear me. And we can just do the lesson without collecting data or anything else. We don't have to do this activity. This is a choice. You need to be able to hear when I say time. Are we ready to release? All right, release in 3, 2, 1, go. And time. Reset. Get ready again. Write it down. Reset.
Mr. Hudson, can we take turns?
Sure, but you need to be quick. I don't care. Yeah. This is not going very well. I expected that you guys would be able to handle this. It's my other classes that I'm worried about. Reset. We're releasing in 3, 2, 1, go. Stop. Lay it down real quick. Crank it. We are releasing. In 3, 2, 1, go. Time.
Okay, it's my turn, or is it?
Reset. Crank it.
No, it's my turn. It's my
Reset.
Oh, wait, that's not gonna work. I'm like breaking it while it's like vlogging. He's so sad.
Do we have issues that we need help on?
No. Don't break
Ooh, then you're all confused because you're waiting for a third class. That works better sometimes. Reset. Crank it. Back to 0. We are releasing in 3, 2, 1, go.
Oh my god, are you kidding?
And time. How many more trials do we need? A couple more? Okay. You can stop. You're like, so, hey, chill for a second. Once your group has like 4 or 5 good data points, like you trust it pretty well, like you're good. But we're going to run this at least a couple more times to let people have a chance. So crank it. Crank it. We're releasing. In 3, 2, 1, release. And time.
6.5. It's been like 1. And then
Reset. Reset. All right, release in 3, 2, 1, go. Time. Do we need more? Reset. Reset. Release in 3, 2, 1, go. Time. Anyone need more? Anyone need more? All right, one person returns everything. One person returns everything. Now, you got... You've got some really important decisions to make. And based off the difference in sizes of your graphs, some of you may be deciding these things differently. You must decide, based off how far your toy went in 5 seconds, how tall your graph actually needs to be. Right? So if my toy went 6 inches, which we're going to talk about how to deal with inches in a moment, in 5 seconds, I shouldn't just make my graph go that high because I need to do my graph out to 20 seconds. So, here's the deal. A lot of you had inches because we had yardsticks. If you had inch measurements or centimeter measurements, what you need to do first, and I'm going to release you guys for like 5 more minutes just to work on your own, average them out, right? Add them all up. Divide by however many you got so we can find an average length that it went. You guys with me? Can we set that down? I don't have very many of those, and I just feel that it's annoying. Then, if you have inches, multiply your inches by 2.54, because that's your conversion factor. if your measurement is in inches, so if I had 6 inches, I would need to do 6 times 2.54, because that's my conversion factor, and I would get like 15 something. I would get over 15 here. Then, hey, I hope we can deal with multiple instructions at once. Then scale your graph. And if you've all made it relatively the same size, your scale can be the same. But if your graphs are different sizes, you're going to have to choose differently. Put your first point wherever it belongs. Create your line to predict where the rest of them go, because it should be straight. If we assume that the toy would keep traveling at the same speed, if they weren't crappy little, like, whatever toys, if it went straight. And then, last thing you need to do is be able to say a y equals mx statement. Because there should be no plus b, because our b was 0. We all started at 0. So your m should be your speed that relates your delta y over delta x, which for us is going to be centimeters per second. This is the very last part, so I'll help you guys with that if you need to, but that's your challenge right now. George.
Okay, so the dot that you put wherever it was,
Yeah.
that's the average, right? Of all
Yeah, the average of your trials, how far it went for 5 seconds. So the only thing that matters is this should be directly above your 5. How far up it is based off your scale and which toy you had. Like, you all are going to get different answers. And real quick, try to write down what toy you had. So there was like blue dude. There were a couple of these blue dudes. And then there were a couple of these robots. But then the other ones were unique. There were no matches for the other ones. I'm going to give you guys 3 to 4 minutes to try to do all that. Make your graph, draw your line, try to make an equation.
We had many Optimus Prime.
You cannot do that. It went backwards. Okay, like turn yourself around. So distance can't really be negative, so if you take it like it's a positive. So just act like that's how far it went. It doesn't matter what direction it went. But like, so try to make some kind of prediction. Really, like, you wouldn't have to collect this from an actual experiment. You can
Not
make
right.
like for real, if you just want to say that your toy travels 6 inches, you can say 5. You just did that to try to
What you guys told me, then you guys just made a mirror.
No, try not. No, it's because she put it on the table backwards.
multiply it by 2.54.
You would be a rebel and not.
Yes.
22.5 is our answer plus 5.
You don't need to do it all out.
And then 5.
So I have a feeling that a few of us need some help. So, Gwendolyn, thank you for volunteering. When you're the loudest person in the room, sometimes you volunteer. So, when you added up all your distances and divided by how many you had, what was your average?
6.4.
And that was inches? Yes? So they got 6.4 inches was their travel. But we have to convert that, so we multiply it by 2.54. Don't forget that 4, it's actually kind of important. Yeah? Yeah, it's 2.54, it's not just 2.5. So, Olivia, what'd you get there then? The 6.4 times 2.54. 16.256. So I know that that's for 5. How can I make a prediction for my 20 seconds? Yeah, multiply it by 4. So what would that be? So that's for 20 seconds. So when I'm out here, I need to be at least at 65. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tick marks. So if I make each of them, I don't know, 7 could work, 6 could work, 6 could work. 5 won't be enough. 5 won't get me high enough. 5 would get us close. If I make my life easy and just do this by 5s, I won't be able to go all the way, but it'll be close. So then, my points that I'm putting on here. After 5 seconds, I went 16.256. After 10 seconds, I would have gone twice as far. 32. Bless you. How far would I go in 0 seconds? 0. So then I can connect my line, and I wish this had the straight line cheat tool. If you have a ruler, your line will be better than mine. Chloe's like, man, that's a bad line. If you have a ruler or anything straight at your desk, your line will be better, and I can predict based off of that. Now, a really easy way to get our equation. If my change in x is 10, and I can go up to where it actually is, which we said this one would be 32.5, essentially, very close if I round it off. What then is my slope? If I went 32.5 in 10 seconds, how do I figure out my slope, Quinn?
You divide 32.5 by 10, which would be if you...
Yeah. So for this toy, whatever that toy was, it's 3.25. Which toy did you guys have? The one with glass. So that was a unique toy. There was only one of these. So you will probably have different data than this. This is not your data. This is that group's data that I picked on Gwendolyn. So with their data, that's what I got. Yours is probably different. Take a couple moments, make sure that your data agrees with your team.
It's a line.
Have you guys been to social studies? Seems like something weird is going on. There's like kids doing work and kids eating. No, but not at the same time. There's some kids who are having to work and some kids who are eating. It doesn't look fair. But like it's food that Pettigrew provides. I'm just very confused. Like, I think it's a simulation. Is what I'm trying to say. There are many trash cans around here. All right, question. If we were able to turbocharge our toy, right? Turbo toys. So, if we were able to double your Speed's toy, what would be its speed, its new speed in centimeters per second? So, make a new line showing your turbocharged toy at twice as fast. But then, also, if we slow-mo our toy and make it go half as fast. So draw both of those lines here. What if I double the speed of my toy? And what if I half the speed of my toy, like of the original, right? We're impacting the original. Quinn, question or answer, what do you...
I wouldn't call it turbocharged. I would call it boom slash.
You call it what? Yeah.
No. Wait, yeah, it is. No, it's 2.5 more. Or is it 4?
All right, we are running out of time, so let's wrap it all back together. Give me your attention for like 30 more seconds, and I'll get you guys out of here. Here's what we're trying to see, and what we're trying to intro kind of slowly. When we work with proportional relationships, which always has to have two things to make it true. When we look at a graph of a proportional relationship, it has to use the 0, 0 point. Right? The train can't go anywhere in 0 time. My toy can't go anywhere in 0 time. That 0, 0 point has to be there. And also, when I graph it, the line must be straight. So we're working with proportional relationships, right? 0, 0, straight line. What you should now have is the original speed of your toy graphed on your middle line, essentially. What your speed would be if it was halved, which, guys, I could just take this point and cut it in half and shift down to that. Likewise, I could take that point and double it and just go straight up to it. So actually, I should have been over one line. I got a little off. But that's how we can manipulate that speed, because our speed is really our slope. And here's what I need you to hear. So give me your eyes. This is also called the constant of proportionality. So it's in our textbook right here. I keep going to the wrong tab. Whatever you're multiplying by, that's your constant of proportionality. So our speed for the train, what was your constant of proportionality for the train? What was it? What was our miles per hour? The 150, right? For the train, our constant of proportionality was 50. For your toy, some like number like 3 or 4 or 5 or 6, something like that, like some smaller value. For my car when I'm driving on the highway, constant proportionality is 65. For my car when I'm driving around the town, if I'm at a constant speed, it's like 25. Right? Whatever your multiplier is. That's all the time we got for today. Have a great day, guys.
Will you be at here?
So, why can't I trust you on your computer, man?
I'm always giving stuff out first.
I know, but why? You know that. I appreciate that you didn't like try to hide it, but what were you doing? So, I want to chat with you later about that. Come and see me at some point to get your computer back so we can talk, okay?